And we're going to put a positive, and we're going to ground here this platinum surface. Now, these electrons on the tungsten, they're in this environment of a negative potential. And that's a high energy state for them because they're negatively charged particles. So if I were to draw here an energy level diagram, I'm going to represent then the energy level of the electrons here in this tungsten, or on this tungsten tip, as some high energy over here. So there's electrons on the tungsten. Whereas the electrons associated with the platinum and the CO here, all of which are in contact with each other, well, they're at ground. That's a lower energy state for these negatively charged particles. So we're going to represent it by this. So this is the electrons on platinum. And so this axis here is kind of a distance axis, right? These are the electrons on the tip. These are the electrons on the platinum. We're measuring kind of distance here from here to here in the vertical direction there. All right, so there's a thermodynamic driving force for the electrons on the tungsten tip to want to be here on the platinum. Okay, but the problem is that this tungsten is not in contact with this oxygen end here. There's a gap. And if this is in a vacuum, we call this a vacuum gap. And so for an electron to be inside of this vacuum gap, well, that's a very high energy state for those electrons. And so if we were to look at an energy level diagram here, that energy actually goes up pretty high before it comes back down. There's a barrier to getting the electrons from the tip to the platinum surface. Well, you've seen this kind of reaction coordinate before. You have, I'm sure, if you look at an energy level diagram here for some reactions, sometimes you have reactants here at a high energy and products here at a lower energy. And in order to get from reactants to products, there's a barrier, an activation energy barrier. You called it E-act or something like that, right? And you know that in chemical reactions, typically what you've got to do is you've got to put energy into the system in order to get over this barrier before you get any energy out, before the reaction can proceed. And that is what happens in a lot of chemical reactions. There's a barrier, and you got to supply that energy to get over it before you can make the reaction go. But over here, in the case of electrons, hey, those electrons don't act like atoms and molecules do for the most part. These electrons, what do? Hey, they ignore this barrier, and they tunnel right through the barrier. Go right through that brick wall. How can they do that? Well, they can do that because they are quantum mechanical particles. We cannot treat those electrons like we treat atoms and molecules, which for the most part behave as classical particles. And actually, this is going to be the subject of the first few lectures here, the need for this new kind of mechanics to explain phenomena like this and to explain chemical bonding. All right? So these electrons tunnel right through. All right, so what does that mean? Well, what that means here for this experiment is that if I then take and I attach a wire to the tungsten tip and a wire to the platinum surface, and I put an ammeter in between, I will see a current. I'll see a measurement of a current. There are electrons going from this tungsten tip to this platinum surface. So I measure a current. Okay, well, that's nice, but now from that, how do I get this image of these 28 CO molecules? Well, what I do is I also have this tungsten tip mounted not only on a piezoelectric crystal that allows me to go up and down, but another piezoelectric crystal which allows me to move it from side to side with control on the order of an angstrom. So I can take the tungsten tip and I'm going to move it over by a certain amount. And exactly, I'm going to know what that certain amount is because I've calibrated my piezoelectric crystal. All right, but now when I move that tungsten tip over, what's going to happen to this current here? Pardon? It's going to go down. It's going to plummet. It's going to go to 0. Why? Because when I move this tip over, I increase the distance between the end of the tip and the oxygen end of the molecule. And when I increase the distance, what I do is I make this barrier wider, right? And the wider the barrier is, the more difficult it is for those electrons to tunnel through. And so the current actually goes down. So to compensate for that, I'm now going to take the tungsten tip and I'm going to move it down by just enough such that I reestablish the current that I originally have. And of course, I know exactly by how much I moved it down because, again, I have my tip calibrated. All right? Okay, so I got 2 points now. I need a third point. So I'm going to take that tungsten tip and I'm going to move it over again. All right? And again, the current's going to go down. But in order to reestablish the original current I had, I'm going to move this down further. Okay? And again, I'll know exactly how much I move the tip over, and I'll know exactly how much I move the tip down. So to get that image, I'm going to provide a color code. I'm going to say that when the tungsten tip is the largest distance away from the surface, well, then that's going to show up here on this picture. It's going to show up as a very light color, right? That's the highest point. When the tungsten tip is a little bit closer to the surface, well, that's going to show up as the darker colors. And as it gets lower and lower and lower, it's going to be deeper and deeper orangey. And finally, when I'm actually tunneling to the platinum surface instead of the CO molecule, hey, I'm going to make that a blue color. All right? So that's how we get the image of this molecular man.